Good afternoon. Today I'd like to demonstrate the calculations of flexure stress in a cantilever, and the cantilever profile is defined by this function y squared equals 400x, and we'll just determine that that's the profile mirrored about the y-axis, and then those two mirrored about the x-axis. And we'll do both the manual calculations, and then we'll compare those values to the FEA in a SolidWorks simulation. So the cantilever is 10 meters long. It's restrained on this end, and it has the weight of the beam itself, the weight of the cantilever, plus a 5 kilonewton load on the end. And so we'll determine the area moment of inertia in the cross-section of the cantilever. And we'll use calculus to determine that. We'll then sketch the shear and bending moment diagrams of the beam, the cantilever. We'll determine what the maximum bending moment is from those diagrams. And then from that maximum bending moment, we'll calculate the bending stress, the maximum flexure stress, and then we'll do the CAD calculations and compare those values. So the section properties, be well to first calculate the area underneath this curve. And so by doing an integral with a vertical element, we can say that y is equal to, if y squared is equal to 400x, then y is equal to 400x to the 1/2. Let's ignore this because that's the value of the function in terms of x. So let's just ignore that one. So that shouldn't have an equal sign there. So our area, using this function, our area is dA from 0 to 100. The length in this distance is 100. And dA would be y dx, and y is 400x to the 1/2 times dx. That's the area of the element. And then we go from 0 to 100. So square root of 400 is 20, and then x to the 1/2 becomes 20. X to the 1/2, integrating that becomes x to the 3/2 over 3/2 from 0 to 100 is 13,333 millimeters, or because there are a million millimeters square and 1 meter square, or 10 to the 6th millimeters square and 1 meter square, move it over 6 decimal places, and it would tell us the number of, or the area in meters square. Our y bar, or the distance to the centroid from the x-axis, is y dA over dA, and y tilde, the height of our distance from the x-axis up to the centroid, would be 1/2 of the total height of y. In other words, the function here, y, is up here. So the height of our centroid is 1/2 of that. So we can put 1/2 y, and then our area, y dx, all over our area, which we calculated. We do the integration there, and we find that the area is 0.075 meters. I'm sorry, that the y bar is 0.075 meters. So let's just, for since we're in this, well, we didn't calculate x bar. We won't need that. Let's calculate our area moment of inertia with respect to the x-axis. And using the parallel axis theorem, we can find that the moment of inertia of a rectangle with respect to its base, or in this case, the x-axis of our element, is 1/3 bh cubed. And so 1/3 B is dx, and our height would be y cubed. And so that's 20 times 20 times 20. The square root of 400 is 20. And cube 20, we get 8,000. And then x to the 1/2 times x to the 1/2 times x to the 1/2 is x to the 3/2. And 1/3 of 8,000 is 2,666, 2/3. X to the 2/3 dx. So integrating that, we find that our area moment of inertia with respect to the x-axis is 106 2/3 times 10 to the 6 millimeters to the 4th, or because there are 10 to the 12th millimeters to the 4th, and 1 meter to the 4th, we move our decimal place 12 places to change it to meters. So there's 106 2/3 times 10 to the -6 meters to the 4th. And just for checking in SolidWorks, if we wanted to move it to the centroid, since SolidWorks, the default calculation for centroids is always with respect to the centroidal axis. So if we wanted to just calculate our function of just this portion of our cantilever, we could move it to the x-axis by using this parallel axis theorem in reverse, essentially, because it's this value plus this value gives us the moment of inertia with respect to the x-axis. So our moment of inertia with respect to the centroidal axis would be the area moment of inertia with respect to the x minus AD squared. So that would be the value of our area moment of inertia with respect to the centroidal axis. But this is the value we'd use to then calculate the area moment of inertia of our entire cross-section of our cantilever. And so we just take that value, multiply it by 4, and that would give us the area moment of inertia with respect to its centroidal axis, since the centroid of our cantilever, if we look at this centroid here, would pass right through the x-axis, wouldn't it? Assuming that's our x. So, and it's also the axis of our centroidal axis of this entire shape. So here's the area moment of inertia of the entire cross-section here. And then the total area, we calculated the area for just 1/4 of it, times 4 gives us the area of that cross-section. So if we now calculate our flexure stress, let's first, let's see. Let's calculate the weight of the beam. The weight of the beam, of course, we'd say we get the density of ASTM A36. Look that up, we find it 7.85 grams per cubic centimeter, which converts to 7,850 kilograms per meter cubed. And so if we take our cross-section area of that cantilevered beam times the length, that gives us the volume of the beam. And then the volume times the density would give us the mass. So we find that we have 4,186.7 kilograms, and our weight, our total weight in newtons, would be that mass times acceleration due to gravity, gives us 41,071.2 newtons, and we can just round that off to 41,000 newtons. If we wanted to place that at a distributed load, we could say that that's 4,100 newtons per meter, or 4.1 kilonewtons per meter is our distributed load on our cantilever. And then the 5,000 kilonewtons on the end would give us a shear diagram, as here's our shear 0, and convention is you're starting on your left and moving to your right. We come down 5,000 5,000 newtons or 5 kilonewtons. And then we drop at a rate of 4.1 kilonewtons per meter. And so that total distance is 41,000. So we're already at 5. We drop an additional 41. That takes us down to 46 kilonewtons, or 46,000 newtons. The area underneath this shear diagram, a rectangular section here, we have 5 times 10 is 50 kilonewton meters. The area of the triangle is 41 times 10 divided by 2 is 205 kilonewton meters. So we can add those two together, 205 and 50 would give us 255 kilonewton meters. And because this is a triangular shape here in our shear, we get a parabolic shape in our moment, and the maximum moment is 255 kilonewton meters. So that will let us calculate the flexure stress using MC over I. So our maximum moment, 255 kilonewton meters, is 255,000 Newton meters. I should put an N.M there, Newton meters, times the distance. Well, the distance that we're concerned about, of course, is from the central axis to the top or bottom of the beam. That's where we get the maximum stress. Bending down, we get maximum tension at the top and maximum compression at the bottom. And since it's symmetrical, we can just use this distance here of the 0.2 meters or 200 millimeters, and divided by our area moment of inertia, which we calculated as 4.267 times 10 to the minus 4. That was calculated right here. So those values give us that the maximum stress is 119,531,250 Pascal, which is approximately 120 megapascal. Looking up the yield strength of ASTM A36, we can see that it's approximately 250 megapascals. So our factor safety would be the 250 divided by our 120, which gives a factor of safety of just about a little bit more than 2. So that's our manual calculation of the flexure stress in that cantilevered beam with the weight of the beam itself and the 5 kilonewton load on the end. Let's try this in SolidWorks. Okay, well, let's demonstrate the stress analysis of that cantilever in SolidWorks. And to create that cantilever, I sketch on the front plane, and in that sketch, I use the not insert, but go to the spline equation-driven curve. And in that equation-driven curve, you can put in this equation here of 400 times x to the power of 1/2 in parentheses from 0 to 100, and make sure that my units, so I can put those in millimeters. I've changed it to meters here for the rest of the beam, but then I use that profile to create the complete cross-section here, mirroring those profiles about the y-axis, and then those two about the x-axis to create the profile, and then extruding that and adding a plate on the end just for visualization and appearance purposes. So once I have my cantilever in the system, I would make sure that my simulation package is loaded. If it's not, you can go to Tools, Add-ins, and make sure that your simulation, SolidWorks simulation, is loaded. So once I get those in there, I create my simulation study. We'll do a static analysis and just say simulation static, And then material, apply material to all. This beam was made out of ASTM A36. So let's scroll down to the A36 steel. Let's see. Thought it was in here. Don't see it right now. 16. Steel. Oh, there, right there. We'll apply that and then close. And so we've got the material, then loads and fixtures just restrain this end. Again, this end is not going to make that much difference in our total calculation. We could have just drawn it to there and restrained that end under the fixed geometry. And then we'll place our load, simulation, come down here to force. I'm going to place the weight of the beam right on top of that. So my edge is selected. I'm going to say the selected direction for the total weight was 41,000 newtons. And the direction is going to be with respect to my front plane. And let's reverse the direction so we get it coming down. So we have 41,000 newtons placed, distributed across the full length of that beam. And then we're going to place another load, a force out here on this end. Just pick that end right there. And again, it's going to be a selected direction with respect to the front. And we'll say 5,000 newtons. 5,000 newtons, and reverse its direction. So you can see that it's now coming straight down. So there's our two loads, distributed load and our concentrated load on the end. So now all we need to do is just mesh and then run our simulation. So I select the simulation mesh control and then pick the top name of my part, so it places that in the selected entity. So I've got my entire part selected. And let's increase the resolution just a little bit and say OK. And then simulation, mesh, create. Increase the resolution just a little. You can try several iterations there with different sizes of elements to see if that impacts your analysis. But you usually will converge at a fairly common number. You'll see that changing that resolution does not change it very much. But the tighter the resolution, usually the more accuracy and the longer it takes to run the simulation. So once we have those, we can then just say run. And we get our maximum stresses here, the von Mises stresses, newtons per meter square is Pascal. This is times 10 to the 8th. So we do have a stress riser here where the sharp corner there interacts with this plate or with our restraint, and it would be the case whether we have the plate there or not, but where it's restrained. And so we get a little spike in our stresses, but it looks like the average is about 120. So you move that over 2, that'd be 120 times 10 to the 6th. And that's exactly what we got. We got 120 megapascal in our manual calculations. Come back here to our manual calculations. See, we've got 120 megapascal. So, and that's what we're getting here. A couple of other things you can do if you want to probe this. You can go to probe and find out what the stresses are here along the beam at different places. It tells you what the node values are in newtons per meter square or in Pascal. You can also animate this for the stresses. You can save that off as an AVI. You can right-click on displacement and show how far it would actually displace You could do that manual calculation as well. Looks like that it would displace about 8 millimeters down from the end. So our deflection on the end would be about 8 millimeters. And we can also show the strain if you'd like. So a good way to validate our manual calculations, or if we're doing stress analysis in CAD, it's always helpful to do an estimate or complete calculations manually, just to make sure that we have made the right assumptions in our CAD model, and help us validate the numbers in our stress calculations.